Clearly audible now? Screen is visible? No replies? At least anyone reply? Am I clearly audible? Screen is visible? Okay. So let us start with the today's class. So today, first let us revise what we have studied day before the yesterday. So because of my extra work yesterday, I couldn't conduct lecture. So today, this session as well as middle session, I'm going to conduct. So in the first session, we will cover a seventh chapter. That is the next point. Right now, we are in the first point only. That is the locking protocols. So in the first session, we will cover a theory part, and in the middle session, we will cover a implementation part of one of the experiments. Okay. So let us start with the today's class. So yesterday, that is day before the yesterday, in the last class, we have seen locks. That is how we can automatically acquire a lock. Wherever there is a no lock, then we can go for acquiring the lock. So here explicit statements are not required for a implementation of a lock. So that care is taken by the same system, that is the automatic acquisition of the lock. So here we have seen the both cases, how we can acquire the read lock as well as how we can acquire the, that is shared lock and exclusive lock in case of read and write operations. So this point we have seen into the last lecture. Also in the last lecture, we have seen about the lock conversion, that is from shared to the exclusive and from exclusive to the shared. So in first phase, that is growing phase, we can go for the upgrading from shared to the exclusive. And in case of shrinking phase, that is a downgrade, we can go for the downgrade, that is from exclusive to the shared. So these points we have seen into the last lecture. Now let us start with the next points in the syllabus. Implementation of locking also we have seen. So lock manager is responsible for accepting the lock and unlock request. So here whenever any transaction wanted to access any of the data items, these will send lock request to the lock manager, which is a process which is handling that which elements or which data items are accessed by which of the transactions. Okay, and hence this will decide whether to grant a lock or not. So locks can be shared and exclusive, so it will maintain a track that which item is held by which transactions and in which mode. So shared lock, and here which transactions are waiting for that queue is also maintained by this lock manager, and it maintains a data structure, that is a lock table, which keeps the all the track, and on basis of which our implementation will start. That is implementation of a two-phase locking is enabled. So this also we have seen. So here how to, it means I had not answered how to differentiate that right now my growing phase is there and right now my shrinking phase is there. Okay, so here in order to know that which is my growing phase and which is my shrinking phase, so there is always a lock point. So I will show you the example. So consider that this is not a two-phase schedule. I will shift to some another schedule. Yes, this one is one of the schedules where we can go for a uh, two-phase locking. So there are two phases in the two-phase locking protocol. The first one is a growing phase where system acquires a lock on the data items which are required by transaction, and during this phase it doesn't release any of the locks. Okay, no unlock requests are sent to the lock manager. And in case of unlock, which is a shrinking phase, only unlock requests are initiated, no lock requests are sent. So here, when we can say that my growing phase is there, when we can say that this is a shrinking phase, etc. So always there is a lock point in the schedule. Lock point, it means that wherever my last lock is there, last lock request is there, that is acting as a lock point. For example, let us take a transaction T3. So T3 may be having any number of the statements, any number of the data items. If consider this was the last lock request in complete transaction T3, then this will be acting as a lock point. Lock point is the last statement where the lock request is same, and shrinking phase wherever my first unlock request will be there, that will be beginning of a shrinking phase. But there is no, it means when we are beginning with the shrinking phase, there is no any question. But in order to know that here we are end with the growing phase, this is declared as a lock point. Okay, this was the point remaining, that is lock point I wanted to discuss here. Still people are joining, almost 15 minutes are over. Okay, now let us, this was the point which I wanted to say, that is lock point. So lock point, wherever my last lock request is there, that will be called as a lock point. And wherever we are having the starting of a unlocking first statement, then there is a start of shrinking phase. Okay, so we are in the first point of the syllabus, that is a locking. Yet many points need to be covered. So let us move fast to the next point. So next we are moving towards a graph-based protocols. So graph-based protocol, it means that instead of having a linear structure, that this this item is held by some another transaction, this item is held by in exclusive mode by some another transaction. Here we are using a data structure called graph to represent a structure of weighting. That is a structure of elements held by a transaction. So here this is an alternative to two-phase locking protocol. So consider that here we are introducing a concept of partial ordering. Partial ordering, it means that whenever we are having multiple data items, within that, if consider there are items like A, B, C, D are there, these are the data items which a transaction can use. Then here we are introducing a partial ordering. It means that here it makes some mandatory conditions, like before accessing B, you should use A. That is, in order to access B, the initial order is that I should access A. So this means that here, unless and until I access A, I cannot go to the B. This is called as a partial ordering. So if such partial orderings are introduced, then if consider transaction T1 is there, who is willing to access B. Now T1 will know that yes, before accessing B, we should go for accessing A. Then in that case, whenever transaction T1 is accessing A and hence B, then simultaneously another transaction may request for a B. So transaction T2 will also know that yes, before accessing B, we should access A. So here partial ordering, it means that here we are introducing a connection between the data items. So this connection between the data items is represented by using a graph. Okay, and graph, these are showing that which elements can be accessed or which are the previous prerequisites which need to be achieved in order to access a next element. So the graph-based protocol says that impose a partial ordering by using an arrow on the set, that is set of elements D, where we are having capital D equal to D1, D2 up to DH of all the data items. Then here, if DI is partially ordered before DJ, then any transaction accessing both DI and DJ must access DI before accessing DJ. So here it means that before accessing DJ, we should must access DI initially. So here this implies that the set D may know, it means D will know that now be viewed as a directed acyclic graph. Acyclic graph that yes, after D1, D2 is going to access, after D2, D3, and hence up to D and DH, etc. A transaction can access the elements. And if such ordering is mentioned, there will not be any cycle available between the data items. And hence, this acyclic graph is called as a database graph. That before accessing D2, we should access D1. Before accessing D3, we should access D3. So this order can be not necessarily be sequential. This can be a tree order also, just like a tree data structure we are having. Non-sequential order also we can access. For example, for accessing D3 and D4, we must access D2. So here it means that, but there is no any relevance between D3 and D4. So such possibilities we can introduce so that a lock can be given at the start stage only, and hence this will help us to reduce a algorithm, that is handling concurrency in much more difficult way. So tree protocol. So this tree protocol is a simple kind of graph protocol. Read this for a minute.
काम नाही माझं काय त्यांना ठेवते की मी वर तुमच्या जमत नाही बरं 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 तुमचं काय असेल
Done with the reading? So this graph based protocol over. Now this is a tree protocol. So here main difference is that here we are having only exclusive locks. Exclusive lock, it means that if a transaction is willing to access a data member directly, it should be for a exclusive lock only. If reading is there, then directly a transaction can request for a reading, but no lock is required. If that data item is not locked, then it can read the data item. If it is unlocked, then any number of the transactions simultaneously can read that data item. Okay, so that is the difference between two-phase locking protocol and tree protocol. And here, sorry, I'll move to the last slide. And here, only exclusive locks are allowed. And here, if consider transaction TI is willing to access item D. Okay, so D is one of the data items which TI wanted to access. Then here, whatever the childs of D are there, C, G, J, these will be automatically locked by the same transaction. Okay, if transaction T wanted to access D, then whatever the childs of the same node are there, that will also become the part of a lock. This is the first point. Next, if there is one parent of D, that is B, so here A is a root element, B, C are the childs of A, and B is having again three childs D, E, F, and then so on. So here, whenever a transaction TI wanted to access any of the item in a tree, then it should make sure that it is accessing or it has also locked the parent of the same item. Okay, it means if a transaction T1 is willing to access element D, then T1 should make sure that right now B is also locked by the same transaction. Okay, whatever the parent of the same item is there, then that should be also need to be locked. And there is also one more restriction is that in case of two-phase locking protocol, we may go for locking and unlocking. Sorry, not in two-phase, but in normal procedures, we can go for locking and unlocking that element subsequently. It might happen that transaction T1 has accessed A, that is by locking, then released A, and then again the same transaction is willing to access the same item A. So it means that multiple locks can be applied, that is at different times by a same transaction on that data item. But in case of tree-based protocols, we doesn't allow to lock and unlock the same element repeatedly. In a complete execution time, a transaction can lock that element only once. Graph-based protocols. The tree protocol ensures conflict serializability as well as freedom from the deadlock. Yes, as there is no circular waiting will be there, as parents are the main source to reach to the nodes. In that case, so here it ensures that there will be, it means conflict serializability can be achieved by this protocol, and unlocking elements at the earlier entry protocol than in two-phase locking protocol. So here elements will be unlocked before locking other items also, because it follows the lock request in exclusive mode, and there is no restriction that it is having some growing phase or shrinking phase, and that's why unlocking may occur at the initial stage also. And here this is having the advantages like this is having a shorter waiting time, then increasing concurrency as we are creating a child structure, then we can whatever the childs are there, then we can go for number of transactions to access those elements at the different leaf layers. Okay, so it need not to be very it is not very complex, it is not very time consuming, so this takes very less waiting time. So it means it might happen that transaction Ti is acquired a lock on D, transaction T2 has acquired lock on E, another transaction might have might be willing to any other item in the parallel or in the same state, and hence concurrency can be increased here as there are multiple childs are there, and so many locks or so many transactions can acquire lock on those items. Next, this doesn't have any deadlocks, and hence no rollbacks are required in the graph based or tree protocol. Then which can be the drawbacks of the same system? So here, yes, we know that there are no rollbacks, but it doesn't guarantee any cascadeless schedules. Yes, there are some schedules which are cascadeless. For example, if a transaction T1 has made some changes at the leaf level, then those changes may be accessed by some another transaction, and hence it doesn't guarantee that a transaction will commit after performing the changes, etc. As in order to increase the concurrency, we are allowing multiple transactions to access the same elements, and hence this doesn't guarantee that there will not be any cascadeless schedules. Yes, there can be a cascading schedule also. So here the solution can be that we, after committing the transaction only, then only that whatever the element we are accessing, consider T1 has performed some changes and T2 is accessing those changed elements, then we can introduce the commit dependencies, just like T2 will commit after the T1 has committed. Such dependencies also we can introduce. And And one more drawback is that as this is having a tree structure and we are having mandatory that we should also have a lock on parent. So unnecessarily there is much more locking done on data items, which may not be used in the transaction at all. So this can be also a drawback of the system, that we are accessing those or we are acquiring locks on those items which are not as a part of transaction. So unnecessarily much more complications will be get added. And we are accessing the parent from the parent level, and hence instead of executing three transactions simultaneously in case of non tree protocol, here we might execute only two transactions. So here there is a decrease in the level of concurrency also is available. Read this slide for a minute. Now let us start with the second point in the chapter, deadlock handling. So previously also we have started with this point. So this was just an introduction as we have started with the new chapter. So in detail, let us see what is meant by a deadlock handling. So deadlock, this term already you have used. So deadlock, it means that a sequence of transactions are waiting for each other, and hence a system cannot proceed with either of the operation. If this is the condition, then we can say that our system is in the deadlock state. So for this purpose, we have shown one example here with transaction T3 and T4. And here you can see the lock A, T3 wanted to acquire and T4 wanted to acquire lock on shared mode in on data item B. So both are waiting for each other to release the lock, and then only a transaction can use those items, or maybe for reading or writing purpose. So what can be the ways to prevent a deadlock? So there are multiple ways to handle the deadlock. First thing is that we can go for preventing a deadlock. That is before that situation doesn't arise that we should have a deadlock. So this can be a best way to achieve the uh, consistent system and achieve the aim for using the maximum resources. And if a deadlock occurs, then we can go for handling the deadlock. So here deadlock prevention, this ensures that system will never into a deadlock state. So this is the best way to deal with the deadlocks. That is, we should have a preventive strategies. So here, the first way is that we should have, it means before start of the transaction, we may send request for all the data items which may be required during the transaction. It means that there will not be any waiting of transaction for any of the item. That is, a transaction is executing and then waiting for any of the item. So this condition will not be there, and hence this can skip a circular wait. As there will not be any waiting, there will not be any circular waiting, and hence the system will not be into a deadlock state. So this is the first one, but it might happen that a transaction may be having, that is, a transaction is lengthier, and initially only at the start only this has acquired a lock, and the data item is required for only few of the operations, and hence that item will be get locked for longer period of time, and hence again a concurrency will be reduced. So it means that this also, it doesn't give us any performance increase or performance throughput increase, but this can be a way to avoid the deadlock. So this is a first way. Next is that we can introduce a partial ordering of all the data items and require that transaction can log data items only in order specified by the partial ordering. So we already seen in graph-based protocol what is meant by a partial ordering. Partial ordering, it means that in order to access any of the element, there are some elements which need to be accessed previously. Just like if I wanted to access D, I must send request to a parent, that parent of that node, and say that yes, I need to access D. Now give me log on C or B also. So this can be one of the ways that introduce a partial ordering and then partial ordering and then use those elements. Next, there are also other preventive strategies are there. So these are the all graphical representation protocols are there. So graphical representation, it means that tree is also having a graphical representation, but this arrow in the graphical represents some another concept, and here this represents, these protocols represent some another concept. In case of graph-based protocol, this shows a partial ordering or element dependency between the elements of a data item. But here it means whether there is a wait or circular wait or transaction wait, it doesn't deal with the transactions, only ordering between the elements it works. But when we start with the wait die scheme, so this is one of the strategies which is used for preventing a deadlock. This scheme is non-preemptive. Non-preemptive, it means that, so here whatever transactions are there, these are differentiated as per the time, that older transactions and young transactions. Young transactions are recent transactions and older transactions than the recent transaction which started in the past very long. So here in wait die scheme, the scheme says that older transaction may wait for younger one to release data item. Okay. For example, if I'm having a transaction T1 which started at 10 a.m. and there is transaction T2 which started at 11 a.m. Now here the T2 transaction becomes as younger. Right now I'm having only 10, after 10 there are only 2 minutes past. Then we can say that T2 is younger transaction and T1 is older transaction. So this is the concept. Now this scheme says that whenever there is an old transaction, this will be waiting for young transactions to release data item. So it means T1 should wait for T2 to release the item and then T1 can start it works. Then younger transactions never wait for older ones, they are rolled back instead. If consider T2 is willing to access data item A and the young transaction T2 is willing to access transaction T2, sorry, data transaction T2 is willing to access a few data items held by the T1, then in that case T2 younger one is waiting for a older one. Then this waiting is not possible in wait and die scheme. So in that case, T2 will get aborted or it will be get rolled back. And here drawback is that a transaction may die several times before acquiring a lock on B. So this can be also a condition. Next, wound wait. So in the previous game, either younger transaction, that is older transaction waits, and younger transaction dies, that is rolled back. But in case of wait and wound scheme, this is a preemptive scheme. Preemptive, it means that the transactions which are having the higher preference will be given, will need not to wait, they will get the data items immediately. But in case of non-preemptive, first come, first serve, this strategy is followed, and hence there will not be any priority, etc., priority based scheduling, etc. In the wound wait, whatever older transactions are there, these will be called as wounds. That is, these need to be rolled for back forcefully of younger transaction instead of waiting for it, and younger transactions may have to wait for the older transactions. Okay, so exactly reverse of first wait die scheme. Here, younger transactions will keep on waiting for older to complete the execution. And here, this will have very less rollbacks as compared to the wait and die scheme. And in both the cases, wait die and wound wait. So here, whenever a transaction is rolled back, then a transaction start with the previous timestamp only, that is original timestamp only. Read this slide for a minute. Still people are joining. Done with the reading? Now let us start with the next slide. So another one of the scheme is timeouts, timeout based schemes. So timeout, it means that how many times. So this might happen that the same transaction is kept on waiting for any of the data item to release. So here, what your waiting time is there for a transaction to release a data item to be get free. So there is a time limit decided for this. If during that period a data item can be accessed by the transaction, it will be allocated. Else the transaction will be rolled back. Okay. So here it means that a fixed time interval is decided, and hence based on that only this will decide whether to continue the waiting or whether to release the current data item. So here, so this might also result in whenever there is a deadlock. So in case of deadlock also, these such scheme will help, as there, even though there is a circular waiting will be there. So because of this scheme, those transactions which have uh, older timestamp or old, those will be get terminated. So this is the way through which we can use a timeout based scheme. Timeout, it means that transaction T1, consider that transaction T1 is holding data item A and T2 is willing to access A. Then here, in order to make uh, T2 for the transaction T2 data item A to be made available, in that case T1 might declare that T2 is waiting and T1 is having the data item. Then T2, how long it should wait, that is decided upon the time used for the scheme. So this might be having different times as compared to the OS, etc. So timeout based schemes. So this limits how much time a transaction should wait. If there is a deadlock, so this will break the deadlock by rollbacking whenever there will be a timeout. And this is simple to implement. But this might happen that this is unnecessary rollbacking multiple transactions. So here consider that right now duration is 5 seconds for executing a current transaction, and during the 5 seconds, if the scheme is getting applied and which is will be having very less time, as so timeout based is simple as compared to the other protocols. But here, how much time we should have for a timeout based, it means how to decide whether to go for 5 seconds, 6 seconds or 2 seconds or nanoseconds, etc. That is difficult. And here this there might be a possibility of starvation also. So this is regarding a timeout based scheme. Next, dialog detection. How to detect that there is a deadlock in a system? So we already know that there is a circular weightage. So the same concepts are given here with the help of example. So here, what your nodes, it means circles are there. These are the vertices and these are representing a transaction. And wherever there is a arrow is there, it means that if there is an arrow from T17 to T18, it means that T18 is waiting for a T17 to release a data item. Okay, this is a wait for that. T18 is waiting for a T17. T20 is waiting for T18, and T18 is also waiting for T19. So, so this is a graph. So age from Ti to Tj. If Ti is waiting for a lock held in conflicting mode by Tj. Okay. Then next, system is in deadlock state if only if wait for graph has a circle. So here there is no any circle is here, but now here is a circle. That T19 is waiting for T18, T18 is waiting for T20, and T20 is waiting for T90. So this is one of the example that wait for graph is there. Next, so what are the current strategies we have seen? Those were to prevent a transaction. If we are detecting with a deadlock, then some transactions need to be rolled back. So this is the primary solution for handling the deadlock, that we are choosing any of the transaction and that transaction will be rolled back. So rollbacking of that transaction will release data items and hence remaining transaction can transfer those data items. And that's why here choosing a victim is much more difficult situation. uh, Victim to be chosen is it means that so each time the same transaction should not be chosen for a rollbacking. So this may lead to the starvation, and hence we can apply some rules like those transactions which are having the minimum time. Those can be chosen as a victim, and those need to be rolled back. So here again, in case of rollback, there are two types are there. First one is a total rollback, and second one is a partial rollback. Total rollback, it means that rollbacking from current point to up to the very start of the transaction where we begin with the transaction. So begin transaction, this is the first statement which will be total rollback up to the start, partial rollback up to the last save point. This will be rollbacking. So rollback determine how far to roll back a transaction. Total rollback about the transaction and then restart it. So this can be one of the solutions, as new timing will be as per the four-wheeler. And partial rollback, it means that up to the save point only. So this will be rollbacking. So rollback victim transactions only as far as necessary to release the law. So this might happen that there are six data items are there. These are accessed by the T1, and T2 is waiting for only one of the item like D only. So it will roll back up to the locking of D only, and then this will start releasing the data items which were accessed by after the statement, after that D's location, and hence this will reduce a complete burden on that data item. Now, so here it can lead also to starvation, because same time choosing a victim, that can be also possible. And hence we can, in order to avoid this, we will make a rule that whatever the oldest transaction is there, that will not be a part of victim, or that transaction will not be a victim. Next is multiple granularity. Multiple granularity, it means that right now whatever relational databases we are studying, this is having different hierarchy. Just like I'm having database, within a database I'm having tables, within the tables we are having columns, and within the columns we are having uh, records or tuples, etc. So here, whenever we are wanted to or we are willing to access a data item, whether to access a complete table, whether to access only single column, or whether to access only single row or single record, or whether to go for keep locking on a complete database. So this shows how much granularity we are having. So granularity, it means that level entry where locking can be done. So here, first subtype is fine granularity. So fine, it means that fine finer entry fine granularity, it means that those elements which are at the leaf level, which are having the lowest level in the tree. And coarse, it means that upper to the current fine granularity. So when let us read what is this. Allow data items to be of various sizes and define a hierarchy of data granularity, that is whether to access single column, whether to access a table, or whether to access complete database. Okay, so where the small granularities are nested within larger ones. Next, can be represented graphically as a tree, but here this is not equivalent to the tree protocol, and hence so this can be represented graphically as a tree. When a transaction locks a node in tree explicitly, it implicitly locks all the nodes descendant in the same node. That is, if we are accessing A, its child D, E, F will be also get a punishment. Granularity of locking, level in tree where locking is done. So first subtype fine granularity, lower in tree, high concurrency, high locking overhead, because as multiple elements will be there in the leaf node. So here again, this is much more difficult to access different transactions accessing at same level. Whereas coarse granularity, it means that this is a high entry, and hence whenever a locking is done, this will not release all the data items one by one. So because of which coarse granularity, it means that higher level in the hierarchy instead of accessing single column or single record. So this will call for a complete record. Complete record. So these are the levels of granularity. First level is database. Second, we are having the area, file, record. Go through this figure and let me know at which level we can say that three transactions can be running. If I'm giving the same scenario, then which can be a database level, which can be a area level, which can be a file level, and which can be a record level. Anyone? Think for a minute. No one is giving the answer. Here, a database represents a complete database. So here there might be very few transactions that might be using a complete database. Okay, for this purpose, this represents a higher level. So database represents a top level where acquiring log or accessing this, it means that you are completely blocking a database. Next comes the area. Area, it means that this might looks like just like we are having a students area, we are having staff area, and we are having some management area, just like if we deal with the university database. Then here our area represents that few of the tables we can represent. Then file represents a table and record represent a complete tuple in a database. So here if consider there are multiple tables are there are multiple files are there. If consider we are having the lower, so here find and quotes, these two are there. Find, it means that lower in the tree, so this will be having a higher concurrency, and course will be having a lower concurrency. It means that here if some transaction is blocking the complete database, then other transactions, even though they are accessing few of the data items, still cannot access the data, because here this granularity has been achieved, and hence whenever a transaction is using this, no other transaction can use this. First thing. Next, if consider they are accessing at the lower levels, that is a fine granularity, then a transaction might work on this FA, stating that transaction T1 is accessing the file A, transaction T2 is accessing file B, and another transaction T3 is accessing file C. So it means that here all these transactions are can be simultaneously running in isolated mode, and hence will not create a problem for a concurrency. Whereas if again it goes to the next level, that is a fine granularity, then consider that right now there are 7 records are there. Then 7 transactions can access those records. So it means that at the record level, again, as we go with the fine granularity, then concurrency can be increased. Database simultaneously can be accessed by a single transaction, whereas area can be accessed by 2 transactions. Again, files can be accessed by 3 transactions, and records can be accessed by 7 transactions. Okay, if we are having the granularity at database, area, file, and record. Whereas if course is given, then course, it means that in the upward direction. In that case, here only few transactions can access those data items. But the thing is that it need not to maintain much more locking, or locking overhead will not be there. For example, handling the locks of 7 transactions and handling the locks of 2 transactions, that makes a lot much difference, and hence whenever we are executing a coarse granularity, this will have a lower overhead of a transaction. And whenever we are executing a fine granularity, then it becomes locking overhead, but we can achieve the concurrency at much more higher level. So this was regarding the granularity. Next, this one is a next intention lock modes. Intention lock modes, it means that in the current phase, we know only there are 2 types of the locks are there: shared and exclusive mode. Shared mode, it means that we can read a data item, and whenever a data item is locked in exclusive mode, we can perform read and write both operations. So in addition to that, at the granularity, it means whenever we are executing a multiple granularity, then there are 3 more types of the locks are allowed. 3 more types. Let us see which are those. So first is a intention shared lock. Intention shared lock, it means that here in future that transaction may have an intention to read any of the data items. Okay, this was the only intention. It means that right now, not right now, but in the future, that during the transaction execution, that transaction is willing to have a lock on that data item. So this always deals with the lower levels of a tree. It means that there are some different locks at the root level, and whatever the lower level nodes are there, which locks we can have on these data items, that is given by this intention lock nodes. So first one is the intention shared, which is represented by is. So this indicates that explicit locking at lower level of tree, but only with the shared locks. Okay, so for example, here, any transaction T1 is executing and this had not locked this FA, then intention shared, it means that transaction T1 will acquire lock IS on record RA1, saying that this in the future might go for reading this record and can lock this data item in a shared mode only. Okay, explicit locking is required. Here, might be used doesn't mean that at the start only you should lock all the elements. Here, intention shared, it means that this transaction is willing to in future might will to go for a shared lock on that data item. So this reduces the possibility that another transaction is trying to have an exclusive lock on the data item. Okay, intention shared, it means that this may be used, may not be used, and hence at a point of time may be requiring to access that element in case of read operation. Next mode is intention exclusive. Intention exclusive, it means that exclusive, we are using for a write operation. So here indicates explicit locking at a lower level with exclusive or shared locks. So exclusive lock, this can be used for read as well as write operation. So here, any transaction which is having a current lock on that uh, current lock on any of the item at level, then whatever lower level elements are there, so these can be accessed in a exclusive mode by that transaction. So this is an indication of that intention exclusive. And next one is a shared and intention exclusive. So which is represented by SIX, which says that the subtree routed by that node is locked explicitly in shared mode, and explicit locking is being done at the lower level with exclusive lock modes. So this seems to be a complicated. So let us see the structure. So they consider that this is a figure. Okay. So right now we are talking about a transaction T1. Transaction T1, if is willing to perform read operation on file A. Okay, transaction T1 is willing to perform read operation on file A. Then here intention shared, it means that this is willing to acquire a shared lock on this file system. So shared, it means that even though this A is locked by some another transaction, this FB is also acquired by some another transaction. So TI is sending the request. It means that T1 is willing to access this element in the shared mode. Then in that case, this request represents that this item can be read by a T1. Next, intention exclusive means that explicit locking for this item in shared, that is in shared or exclusive mode. That another transaction T2 might will to execute or perform operation on this file system. This file, that is FB. Next comes, so whether you are locking a parent or not, this doesn't matter here. Okay, here whenever this FA being accessed by the T1, FB being accessed by the T2, it doesn't make difference whether you are having a lock on A1 etc or not. Okay, and last one is a SIX, stands for the shared intensive exclusive, intention exclusive. This means that here Consider that A2. This is shared. This is locked by transaction T3 in shared mode. Okay, this A2 is being locked by transaction T3 in shared mode. Then here explicit locking, that this the same transaction is willing to access this FC also, or this TC1 also, or TC2 also, then that transaction must also acquire locks on these data items. So in the start only we know that if this is accessing a lock on this, then whatever the childs of that that node are there, these will be also accessed by the transaction. But here intention exclusive this mode, or intention exclusive, or intention shared, or SIX, this is introduced that yes, transaction T3 is also willing to use FC. Transaction T3 is also willing to use this record. If consider transaction is not willing to access this RC1, then SIX is not required for this node. SIX is required for these two nodes. Okay, so this is the meaning of shared intention exclusive lock. That a parent is having a shared lock, and whatever subtree is there, those nodes need to be explicitly locked in a exclusive mode. So let us read the explanation once more. So explanation says that intention shared indicate explicit locking at lower level of the tree, but only shared locks. So this only we are having a shared lock. Next, intention exclusive indicates explicit locking at a lower level. Okay, lower level with exclusive or shared locks. And then next, shared and intention exclusive, the subtree rooted by that node is locked explicitly. Subtree, it means that this subtree I'm talking about. So A2 is our main node, and FC, RC1 and RCM, these are the subtree of this A2. The subtree rooted by that node is locked explicitly in shared mode, and explicit locking is being done at lower level with exclusive mode locks. So it means that here, whatever this tree is there, so that tree will be explicitly locked into shared mode, and then locking can be done in exclusive mode also. So here parent will be in shared mode, and whatever root is there, that will be into a exclusive mode. So I expect you should read this explanation for a minute. Done. So here the main aim behind this intention locks is that even though you might be having a higher level nodes locked into any of the mode, this intention shared, intention exclusive, and shared intention exclusive, these can be applied on the lower level. Okay, lower level at the higher level we might be having that is compatibility matrix we are going to study, but at different exclusive. So intention shared, along with that intention shared, both are performing the read operation that will be allowed. Next, if existing lock on my lower data item is intention shared, then intention exclusive lock also can be allowed on that same data item, and hence shared also, because shared this stands for the only read operation, and hence this can be also allowed. But along with that, if we are having intention shared only on the data item, and if we try to obtain SIX law, stands for the shared intention exclusive, then at this point also this will allow for the reading and performing the changes data. And but if it is only related with the exclusive, that is a write operation, then in that case this will not be a compatible with the intention share. Similarly, regarding the intention exclusive also, so during this sharing of devices, sharing of data, that is a read operation, again SIX and X, these will not be allowed, because here uh, the contents may not be may not be feasible with the writing option and reading operation, and hence at this point also this will not allow any write operation to be performed. Simply intention exclusive, it means that I'm having the same lock and then any other transaction is accessing the data item, then also we can allow. So here main aim is that these requests can be on a different nodes of a data uh, tree protocol. Okay, so here it means that these are the existing lock on the parent of that data item, and these can be the new locks which these are willing to obtain on a child of that combination. So in that case, this is a matrix. So instead of reading and memorizing, please observe the pattern by your own for a minute. Done. Then, how this multiple granularity locking scheme works. So, these are the rules which need to be applied on a multiple granularity locking scheme. So, first one, so you might have observed the lock compatibility matrix. Yes, we have done. Next, a root of the tree must be locked first. Yes, we need to lock the root first initially because unless and until root need to be locked, we cannot go for a child nodes and maybe locked in any node. Okay, so initially we are having any type of lock on a root that is shared or exclusive. Next, a node Q can be locked by Ti. Okay, node Q can be locked by Ti in yes or intention shared mode only if parent of Q is currently locked by Ti in either intention exclusive or shared mode. Intention shared mode. Okay, so here it means that whatever the down level elements are there, just like file records, etc., here in order to access those we must have initially that whatever the parent of f is there, it should be uh, locked in shared or intention shared mode. So this explanation says that here if fa we wanted to access, then whatever a is there that need to be locked in shared or intention shared mode. Then whatever the elements are there or whatever the data items are there, then here then whatever lower levels are there, there we can go for intention shared and intention exclusive lock. That is, we can have transaction ti, this is locking this element, then transaction tj can locking this element. Next rule, a node q can be locked by ti in exclusive, in shared intention exclusive, and in intention exclusive mode if parent of q is currently locked by ti in either intention exclusive or shared exclusive mode. Okay, it means that if we wanted to um, access a child node, then we should have a intention shared lock on the data item. Sorry, intention shared, or we can have exclusive or shared intention exclusive lock on that parent of q. And then whatever childs are there on them, it can apply for a intention shared or intention exclusive locks. Next rule, ti can lock a node only if it has not previously unlocked any node. Okay, that is ti in two phase. Yes, we can go for lock request only when there is unlock, no unlock. And then ti can lock a node q if none of the children of q are currently locked by ti. Okay, so if child nodes are locked and unlocking the parent, this means that this will keep a database into inconsistent state. So before releasing the lock of parent, it should make sure that whatever the uh, components are there, elements are there, that is child nodes, these all need to be unlocked. So here we can make a conclusion that from the higher level to the lower level, we need to acquire the locks, that is from parent to the child. And when it comes to the releasing, from child to the parent, we should move. And next one is this is just a simple definition that a log granularity escalation. In case there are too many logs at a particular level, switch to another granularity shared or exclusive log. Sorry, move to the next slide. Yes, this one is read these rules. So here, this slide is about if consider we wanted to perform insert or delete operation. So whatever data item access we are performing, so that is regarding the existing operations. So up to now only we have seen two operations, read A and write A. So in the write A only we have considered as an insert and delete operation also. But here insert and delete, when it comes to the granularity, so it means how we can differentiate that I am trying to insert a new value or we are trying to remove a value. So in that case, we must take some rules or precautions or some rules need to be followed for these operations. So here, whenever you consider that we wanted to write any of the data item, then it delete any data item, then it is mandatory that there should be an exclusive lock on a data item. Okay, and then only that element can be deleted. Okay, whenever we wanted to delete an item, then it is mandatory to have a mm, then it is mandatory to have a exclusive lock on that data item. Then only it can go for deletion of that value. And second one, whenever we are willing to insert any value, that insert value, whatever the transaction T1 is inserting, that easily, it means simultaneously cannot be accessed by some another. Still, whenever a transaction is performing write operation, that tuple need to be in exclusive mode, locked by exclusive mode, and unless and until that transaction commits, that is not accessible to the others. Okay, so it means that whenever writing need to be done, first we need to give a exclusive mode lock, and then only we can go for inserting of that value, and hence unless and until that transaction commits, we cannot go for using or making that interpol available to the other transactions. So this is regarding the insert operation. So we always differentiate these operations to be write operations. But deletion it means that this is completely removal of value, and hence this there should not be any conflict, etc. Now here we completed our multiple granularity. Now let us move to the next point, that is timestamp based concurrency control. So whatever we have seen, that is regarding the locking, that multiple granularity, deadlock handling, graph based or tree based protocols, etc. So those all were dealing with the locking of an element. Locking, it means that locking that item so that no other transaction can use. So now here we are using a timestamp based concurrency control. So this mechanism doesn't work on a locking of a data item, but this deals with the timestamp or a time based values. So let us see what is mean by this. So here first we need to study what is mean by a timestamp. Timestamp, it means that this is a unique value which is a combination of date and time. So time can be in terms of some nanoseconds or less than that. It means 1 by 10 to the power ninth of a second, or 1 to the 10 power of 12 of second, etc. So it means that here this is always a unique value, the time at which a transaction was initiated. Okay, so each transaction Ti is issued a timestamp Ts of Ti when it enters into a system. So whenever a transaction is entered into a system, at this point this value is assigned to that transaction. So every transaction is having a unique timestamp value. Just like we know that whenever we are performing a banking operations, we always have a unique transaction ID. This transaction ID doesn't get repeated. But here, unique timestamp value, this is assigned by a system to a transaction, which is always a unique timestamp value. We know that any fraction of second cannot be repeated, and hence every second is a different time domain. Similarly, the same concept is applied for a timestamp value. Even though we are saying that concurrent two transactions are running simultaneously, still there will be a difference of some microseconds, some nanoseconds, etc. So those difference will be used for a differentiating between a transactions. Okay, so here a timestamp, remember that this is always a unique value, combination of date and time, and assigned for every transaction that which performs some operations. So here, when it comes to the timestamp value, so we can say that the 5 minute earlier some different timestamp was there. 5 minutes later there will be a different timestamp. It means that whatever the newer, it means a recent transactions are there. Those will be having a higher timestamp, higher time value as compared to the old ones. Okay, old ones, those which are started in a past, and new ones which are right now currently going there. Okay, so and hence the timestamp get rate means that that transaction is that much younger, or new transaction is there. So newer transactions have timestamp slide strictly greater than the earlier ones. Okay, so there are two ways to assign the timestamp value. So real timestamp, real time may not be unique. That it means we are using 1, 2, 3, 4, etc. Then that may not be unique, etc. If we are having a multiple processors, etc. In that case, if we are using a fraction of seconds only, it means instead of microseconds, if we are using a second, then unique value we may not be able to assign. So that can be a problem here, that whatever real time we are considering, that 10:30, 11:30, or 12:30, etc., it contains total 60 seconds, or 60 minutes, and still we are considering that as a single time. Then this time stamp doesn't work for a transaction into a database. Next, another one is use a logical counter to ensure, it means whatever. uh, so here, timestamp could be based on a logical counter. Real time may not be unique, just like I given the example of second. In a second, multiple transactions may come to the system, and hence this may not be a unique. But we can go for fractions of second, and then we can differentiate between this. And second one is can use wall clock time, that is whatever timing within my clock is there, or we can go for using a logical counter also. Logical counter, which will be a global and always having a unique value, to ensure that yes, we are having a unique value. Next, timestamp based protocol manage concurrent execution such that timestamp order in which the transactions are coming to the system in the same order, serializability order will be there. That transaction T1 has arrived at 10:30, transaction T2 as 10:32, and transaction T3 as 10:35. Then we are having timestamp ordering as T1, T2, T3. Then in the same order, we should have a serializable order, or serializability order of the transactions into a data. Okay. So several alternatives are there to how to assign a timestamp value. Right now, we are considering a combination of date and time with nanoseconds or microseconds, etc. The same concept we will use throughout the chapter. So let us see with the protocol. So, or there are only few minutes left. So, shall we revise what we have studied? So in the today's lecture, we moved somewhat fast as compared to the previous lectures.